So I just found this article from Platforming in which they are talking about how they were able to cut down their Node.js memory in half. The memory usage by Node.js, they were able to cut it down by 50% in their application. And the way they are doing it is so simple, yet it is so impactful. So that is why we have to see how they are able to do it. So to understand that, we need to understand a few things about Node. So first of all, we need to start with the node. We will create a node folder here. Then we will have to have a few memory bytes, right? So first of all, as soon as the node starts, it actually allocates 3 memory blocks. This one is basically your stack. All of the function calls, everything, all of that goes on this stack. Then another memory space is allocated, this one. This is the heap. Here all of your variables and other objects are stored. And then there is one more space that is allocated by node, and that is native memory. So we have these 3 memory locations, that is stack, then heap, and then we have native memory. So the stack will contain all of your function call. Every time you are actually calling a function, it is put on the stack. The heap will contain all of your objects. Each time you are creating an object, it is put on the heap. And the native memory is all about buffer. Yes, the native memory works with buffer only. It does not work with any kind of string or integer. It only works with buffer. Now this heap also actually contains a few more blocks. First of all, we have the new space, and then we also have this old space. So in the new space, everything that is fast moving like small objects or these kind of things will be placed here, and in your old heap we will have very large objects or long-term living objects like environment variables or your pointer objects that are pointing to buffers in the native memory. So what is this native memory? Well, native memory only contains buffer, and the main difference between a native memory and a heap is that the heap is actually limited. Yes, the heap is actually limited in the size. You cannot actually grow it arbitrarily large all the time. That is why you will always see these kind of things. The max max old space size. So you will see these kind of flags written in the Node.js configuration. And yes, this flag is literally actually representing this old space memory. So this controls directly this one. You can set how much old space memory is going to be. You can set a defined space. For example, you can set it to be 15 GB or 20 GB or 10 GB, whatever you want. But by default, this entire thing is actually just 4 GBs. Yes, you cannot store more than 4 GBs, even if your system actually have more than 4 GBs inside of it. So you can have a system with 16 GBs of RAM, but the Node.js will crash as soon as you go beyond 4 GBs. So that is why to manipulate the size that the heap can actually take in the RAM, we use this max old space size variable. You can set it to 15 GB or 20 GB, whatever you want to set it to. So that is the main difference between the native memory and the heap memory. Now in the native memory, you are always dealing with buffer. So each time you are doing something like read file, or for that matter read file sync also. So each time you are doing something like this, you are reading something and you are just passing some kind of source, maybe a URL or something. Each time you are doing this, you are actually using the native memory, because your file can be very big, right? Your file can just be simply 50 GBs or maybe 20 GBs, right? So you cannot directly store that inside of the heap. So that is why you are always using native memory when you are reading file. Okay, each time you are doing something like file sync, read file sync or something like that, you are using native memory, because native memory can actually take up all the space that is available in your RAM. It will not crash your Node.js application. But as soon as you go beyond 4 GB and you have not set this max old space size, or basically you go beyond this max old space size limit in the heap, your application will crash. Okay, so that is why the native memory is very important to Node.js. But remember, if you are doing something like this, you are doing read file sync and then you are saying UTF-8. What you are doing at this point is basically you are converting the data in a string. And as soon as you do this, as soon as you convert the data into a string or into a number or a normal data type, you are basically taking the data from the native memory and you are placing it inside of the heap. Okay, and in that case, if it is more than the limit, then it will simply crash it. Okay, simply crash it. So be very careful when you are using this read file sync and read file sync with UTF-8, because remember, the native memory can only store buffer. It will not store any other thing. Okay, but it does not mean that there is nothing stored on the heap for this native memory. So when you are writing code like this, right, you will always have a variable. For example, where my file, right, my file is equals to read file sync and from this particular source. So what will happen right now is that this variable, okay, this variable will actually become a pointer, and this variable will be stored inside of the heap. So basically we will have a pointer in the heap that will actually point to the object that is present inside of the native memory. Yes, this particular object will actually be present inside of the native memory, but this particular pointer will be actually present inside of the heap. And now you might have this question that how is native memory able to grow in size without any restrictions? Well, that is because the native memory is actually taking memory from the operating system itself. So this right here is our operating system. It can be Windows, Linux, Mac OS, whatever you want it to be. And then each time Node.js requires any more space for native memory, it will directly call functions on the operating system to get more memory. Remember that Node.js is actually written in C++. Okay, so Node.js can actually use all the function of C and C++, which means Node.js can actually use the function malloc. And malloc is the function that we use to allocate new space to our program. So each time Node.js requires any more memory, it will simply call the malloc function on the operating system, and then it will get new memory. It can be 50 GB, 40 GB, whatever it is. And as long as your RAM have the memory, the operating system can provide it to the Node.js. And since we have allocated the memory using malloc, we need to deallocate, or we need to free this memory with the use of free function, right? We always have seen this in C or C++. So we need to call this free function to actually deallocate this memory. And how does that happen? Well, garbage collector do this with the help of this pointer that we have on the heap for this particular object. So when we are not using any references for my file in our program anymore, the garbage collector will use the pointer that is present on the heap for this particular read file sync object, and then it will just free it. So that is how this entire thing works. But the thing is that this entire thing does not really have anything to do with that article. This entire thing, you need to understand it to understand. Okay, it is like a pretext. It is like a context that you need to have to understand how they were able to cut down the entire memory expenses in half. So what do you think happens when you are actually creating an object inside of the Node.js? So here we have a very simple object in the JavaScript. So what do you think really happens when you are creating an object with the help of Node.js in JavaScript? Well, there are many things that are happening, and there are many pointers that are being actually created just to handle this particular object, just to handle one single object. One of the pointers that we actually have is this map pointer. So we have this map pointer which is responsible to understand the structure of the objects, because we can always remove and add properties inside of this object because it is JavaScript. So we need a way to make sure that we understand what is the structure of the object or the shape of the object, and map pointer is what does it. Note, this is not the map object that you see in the JavaScript. Map pointer is basically a hidden class that is used by Node.js to actually make sure it understands the structure or shape of the object. Then we have the properties pointer here. So properties pointer, when do we use it, right? So as soon as you actually start adding properties, or as soon as you actually just make random changes in the object by adding properties, by removing properties, like a lot of the times, we actually need this properties pointers. And this properties pointer is responsible to track all the properties that are present inside of this object. Note, if you are actually creating an object just like this, you just give name, age and hobbies in the object itself, and you just created it, there will be no properties pointer, or if it will be there, it will be simply point to null. Okay, but as soon as you start adding more properties, okay, as soon as you start adding more and more and more properties or removing properties, then this properties pointer will come into the picture. It will keep track on what is happening now to the object. So that is why we need a properties pointer. And note that all of the properties, name, age and hobbies, they will be tracked by a single properties pointer. So this single properties pointer will actually point to a particular array or a dictionary. So array, when you are actually not changing things too much, but as soon as you start changing things too much in the object, it will simply switch to a dictionary data structure. But again, wait, that's not it. Okay, we also have these value pointers, or basically all these values that you can see for these properties, they need to have their own pointers. Sometimes, not all the time, but yes, sometimes they need to have these pointers. So we will have value pointers, and for value pointers we will have a value pointer for each value. Okay, for properties pointer we just had this one property pointer that was actually responsible for all the properties, but for value we have one pointer for each value in a property. So as you can see that we have many pointers for this simple object. We will have almost like 1 2 3 and like 5 pointers. Just right now we have like 5 pointers for this particular one single object, with the 3 properties inside of it. So you can see that when you actually have lots and lots and lots of objects in your program, the space that is taken by these pointers will be huge, okay, because each pointer takes around 8 bytes of space. So this map pointer will take around 8 bytes of space, this properties pointer will take around 8 bytes of space, and this value pointer will also take around 8 bytes of space. So now you can see that each of these pointers and 8 bytes each, okay, that is the keyword here. So each pointer takes 8 bytes in the memory to be stored. So you can now guess how much space these pointers will be taking when you have like thousands of objects in your program. So the way Node.js team, or basically the V8 team, because this is the issue that V8 team have, so they actually figured out a way to just reduce this thing, okay. Now what they did is actually reduce this size from 8 bytes to just 4 bytes, which means they are effectively cutting down the space by 50%. So in a way they were able to reduce the memory consumption by Node.js by 50%, and like not completely 50%, but you will always see it in the range of 40 to 50%, like approximately. And most of the time in production applications you will not see this like massive efficiency of 50%, because remember that the pointers, okay, pointers are the only thing that is affected by this thing. So your object still takes the same amount of memory as it was taking earlier. It's just that the pointers are now taking less memory. So mostly you will get like 40% efficiency or 30% efficiency. But yes, if you have a small application which actually like have very little objects, but those objects have more and more and more pointers, then you will see like more than 50% of efficiency in terms of space by Node.js. So that is a massive thing, and yes, this is a very massive improvement. But understand that it also comes with caveats, okay. Yes, they just went ahead and reduced it from 8 bytes to 4 bytes, and that limits how much data you can store in the heap now, okay. So after this thing, after making this to 4 bytes, the maximum data that you can store in the heap is 4 GBs. Yes, and that is not a limit, okay. They did not set this limit. It is actually a mathematical impossibility to store anything more than 4 GBs at this point. So what does it mean, right? Well, what is 1 byte? 1 byte is basically 8 bits. So let us draw this, right? We will have a big byte. This is a 1 byte, and then we will have like 8 bits, right? And 8. So we have around 8 bits here, right? So 1 byte contains around 8 bits, and each bit can actually store 2 values. It can store 1 or 0. So each of them can actually store 2 values. So the biggest number that I can actually store inside of 1 byte, okay, 1 byte is basically multiplication of all these possibilities. So I have 8 bits here. So the biggest number that I can store is basically 2 raised to the power 8. So basically the biggest number that a 1 byte can store is 2 raised to the power 8. Okay, so you have 4 bytes for each pointer. So the biggest number that one pointer can actually store is 2 raised to the power 32. So it will be equal to, so it is basically like multiplying 2 raised to the power 8 4 times, right? Now this 2 raised to the power 32 is actually same as 4 GBs. Yes, if you calculate it, it will be 4 GBs. Now I'm not saying that one pointer can actually store 4 GBs. Okay, that's not what I'm saying. It's a little tricky to understand at first, but let me explain. So when you are actually starting a Node.js application, what happens is that Node.js will actually allocate a memory. So what Node.js will do, it will take 4 gigabytes, okay, 4 GBs of memory, or maybe X amount of memory, like just call it X, okay, X amount of memory. So this contains X amount of memory. Simple. Okay. Now this 4 GB. Why are we saying that only 4 GB is the limit? Well, first of all, this thing, okay, this will actually have a base address from where the memory is starting. So let's just call it base address. Okay. And then what will happen is that every memory or every space that you have will be after this base address. Correct? And remember that an address of a memory is nothing more than a number. Okay, you will always see addresses written like this: 0x000001. Okay, this is just a number. Okay, it's an hexadecimal number that you can convert to a normal decimal number. Okay, and then you can add these numbers. So this is just a number. An address is nothing more than a number. And here we have seen, okay, we have a base address here, right? So a base address simply means that we have a number, okay, an address in the memory from where we are actually starting to allocate memory for the Node.js use, okay. And then when we are saying that a number, okay, when we are saying that one pointer can actually represent a maximum number of 2 raised to the power 32, okay, what this means is that this length, okay, from base address to the ending bit can only be 2 raised to the power 32, okay. That is why we are saying that we can only have a limit of 4 GBs. Let me make it a little bit more clear. You will have a base address. Suppose that 001 is actually the base address that we have, okay. And now you want to actually go to a memory location of a variable. So that variable will be pointed by a pointer, right? Some kind of pointer will be there, right? So that pointer will store the memory location of the value that the variable contains, right? So what is that pointer is storing is simply an address, and an address is simply a number, right? So an address can simply be 0x00000, like just say 2, right? And then what you do is you add these two to get the resulting address x000, not x0, 0x000 and 3. Look, don't look at these numbers. These are just for representational purposes, things. These numbers will be different in the memory, but I'm just giving you an example about how Node actually treats memory. Node will always have a base address, okay, that it will decide before running, and then all the memory that we are going to allocate will be allocated after this base address, okay. So if memory is just a long strip of bits, because that is what it is, right? It is just a long strip of bits that you actually just write to. You can always write 0, 1 to these bits. And what we are saying is that we are going to select a particular bit and we are going to say that we are gonna now start allocating or using memory after this bit. So this will become our base address. And now what we are saying is that after this bit we can only reach a number, right? So this bit will be on a number, like just say 1. I'm just giving an example, okay? And this 1 is just an address. This bit will be 2. So the address of this bit is 2. This bit will be 3, right? This bit will be 4, right? And we know that a single pointer can actually store a value of 2 raised to the power 32, right? Which is a very big number, okay? So it means that we can only go up to 2 raised to the power 32 number, right? Correct? Because that's all our pointer can store. And this 2 raised to the power 32 roughly translate to 4 gigabytes. And that is why we are saying is that we can only allocate 4 gigabytes worth of bits, okay, to our program. Because if we have a pointer A, okay, and that is storing the maximum value, and we have a pointer B and that is also storing the 2 raised to the power 32 maximum value, what do you think will happen? We will take B, we will try to add it to the base address, right? And it will give us what? It will give us the ending address. That's all it will do. And then we will take A and we will try to add it to the base address. That is also going to give us 2 raised to the power 32, this ending bit, right? This maximum limit, that is what it is going to give us, right? So at the end of the day, we can only have 4 GBs of storage available to us. This is a mathematical impossibility to go beyond it, because no matter what pointer you use, we are limited by the number that we can store or the address that we can store inside of the pointer. If the only thing we can store inside of the pointer is 2 raised to the power 32, then each time we are going to add it with base address, it is going to give us the address of the same bit, right? It is not going to go beyond it ever. And yes, like some of you might say that, okay, Satyam, why don't we just have multiple base addresses? Why don't we just say that, okay, we have like 4 base addresses. Okay, we want base address 1, we want base address 2, we want base address 3, right? And we want base address 4. Why don't we just have this? And then for each of these base addresses, we can have 4 GBs, right? For all of them, we will have 4 GBs, which will give us a total of 16 GBs of RAM storage. And yes, that is a very clever way to do this. I mean, it seems like a clever way to do this, but how do you think this base address is stored inside of the memory? This base address is not stored in the RAM, okay? Base address is not in the RAM, okay? Base address exists in the registers. Base address exists in the registers of the CPU, okay? So registers are special hardware that are very fast. They are faster than RAM, and we need this base address because we need to calculate the address. Okay, we are going to add multiple addresses to this base address to calculate the new address on which our value is stored. So that is why accessing and writing to this base address, calculating things should be very fast, and that is why we actually store this inside of the registers. And registers are very small, like 2 KB or 3 KB sometimes that can happen. Okay, yes, I mean in newer models it can actually go up to 1 MB or 2 MB. I am not sure the latest versions, but it is very small. It is very small, and that is why it is important for us to utilize it very carefully, because all the other programs are also utilizing the registers for their purposes. So you cannot go ahead and store 4 base addresses directly inside of this registers. Okay, because that is a very bad thing to do. That will mess up many things. And you know what, even if we ignore the registers problem, we say that we are going to store 4 base addresses inside of this registers. But suppose that we have base address 1, right, and then base address 2, right, and now we are getting a number or an address from a pointer. Okay, so this is a pointer and it is going to give us some address, right? And this is going to be a relative address. Okay, it is not address of the memory itself. Okay, it is a relative address that you are going to add to the base address to find out the exact memory location in which we should go and find out the data, right? So now the question is, where are you going to add it? Are you going to add it to the base address 1, or are you going to add it to the base address 2? That is an ambiguity, right? Where are you going to add it? Right, so you need a way to find out in which location you are storing this particular value, right? In which base address you are storing. So what you will need to do is in this particular pointer. Okay, so this pointer will have a number, and a number is nothing more than bits, right? So it will have 0 0 1 1 0 1 0, right? It will have bits, right? So what you can do is, since we have 4 addresses right now, we can reserve first 2 bits to decide in which direction we are going to go. If we have 0 0, we will go to base address 1. If we have 0 1, we will go to base address 2. If we have, like just say 1 0, we can go to base address 3. Okay, and if we have 1 1, we can go to base address 4, right? But just imagine, okay, now we have reserved 2 bits out of 32 bits to store in which direction we need to go. It means we only have 30 bits left in the pointer, right? So it means only 2 raised to the power 30. Okay, because 30 bits is the only thing that we have now. So this is the maximum number that we can represent with the pointer now, because these 4 bits, well, they are only used for defining where we need to go, and this 2 raised to the power 30 will translate to 1 GB. Okay, it will translate to 1 gigabyte of space. That's all it will translate to, which means that these 4 base addresses will eventually only have 1 GB available to each of them, right? So we have 1 GB here, 1 GB here, 1 GB here, and it means on a complete basis we still only have like 4 GB available to us. So you can see that we are now back to square one, and we actually made it even worse, because now we are storing different base addresses in the register, and we have just increased the overhead in the system, and we still did not get any more memory. We just got the same. So this is a mathematical impossibility right now to actually get more memory with this 4-byte pointer. But yes, people have been trying to figure out a way to solve this problem, and one way that they have found out is that allocating 4 GB of space per thread. So one thread will only have 4 GB of space, but we can have multiple threads running, and each of them can have 4 GB of space for them in the RAM. So we will have effectively more space, like 16 GB, 20 GB based on the number of threads that we have. But still, it is a very good thing that Node.js have been improving a lot, and with this 50% reduction in the memory consumption is crazy, right? So in my opinion, the Node.js is now on the track again to become this go-to option for running JavaScripts on the servers. Like, it is getting more features, it is getting better architecture, it is getting more efficient. So yes, I see that the Node.js have a very bright future. And that is pretty much it for this video. We will meet in the next video. Till then, bye. The name is Shiv Seti.